Okay, let's unpack this. In a world that's just constantly buzzing with AI, LLMs, all this tech jargon, some terms get thrown around so much they kind of lose their meaning, right? They become these abstract things instead of, well, precise tools. Today, we're doing a deep dive into two really fundamental concepts, absolutely central to how AI, how search engines understand language. We're talking tokens and embeddings. Now, you might think these are totally brand new, like hot off the press ideas, especially with all the generative AI stuff exploding lately. But as we'll find out, they actually have a surprisingly long history, a really rich history, especially in, SEO and information retrieval. So our mission today, let's cut through all that noise. We want to give you a really clear understanding of what tokens and embeddings actually are, how they've evolved from just counting words to representing complex meaning, and crucially, why they matter so much for everything, from your everyday Google searches right up to the AI agents of tomorrow. Think of this as your shortcut, your guide to understanding the linguistic backbone of modern AI and how it's changing how we find information, interact with it, create it, everything. So whether you're prepping for a big meeting about AI or just trying to catch up on the latest tech news, or maybe you're just super curious about how this stuff works behind the scenes, we promise you some aha moments. Hopefully plenty of surprising facts to keep you hooked, but without feeling, totally overwhelmed. Let's unravel these concepts together. Right, so to really get where we are now with AI and language, we have to start at the beginning, the absolute basics. So let's talk tokens. What exactly is a token, and why is it considered like the foundational piece, the starting point for text analysis?
Yeah, it's fascinating. It's often kind of skipped over, but a token is, at its heart, really simple. It's just an individual unit of text. Imagine you take any sentence, anything written or spoken, and you just break it down. Chop it up into its smallest, meaningful parts. Those parts, those are the tokens. Could be a whole word, could be part of a word, a number, even punctuation sometimes.
Okay, so like the basic building blocks.
Exactly. They're the elementary building blocks that machines use to start processing human language. Let's take a concrete example, make it super clear. From the source material, right? Sentence. Semantic search improves the quality of search.
Okay.
If we apply a really basic tokenization, maybe just splitting by spaces and punctuation, what do we get? We get semantic search improves the quality of search.
Ah, I see. So each word and even the period at the end, each one is its own token.
Precisely. It's a literal breakdown into the most obvious bits.
But I guess it's not always that simple.
No, definitely not. That's where the nuance comes in, and it's really important. Basic word splitting, it works, it's intuitive, but it has limits. Think about New York.
Right. Two words, but one place.
Exactly. A simple space tokenizer splits them. New York. You lose the meaning of the city. So more sophisticated systems, especially the ones trained on huge amounts of text, they use cleverer techniques. Subword tokenization.
Subword, like parts of words.
Yeah, things like BPE, byte pair encoding, or word piece, they break words down into smaller common units. So unbelievable might become unbelieve and able.
Oh, okay. Why do that?
The real genius there is handling words the model hasn't seen before, what we call out-of-vocabulary or OOV words. If a new word pops up like, say, decarbonization.
Which you see a lot now.
Right. A subword tokenizer can break it down. Decarbon, efferation, it can guess the meaning from the parts it does know.
Instead of just seeing it as a total unknown.
Exactly. It also helps with different word forms like run, running, ran, and it makes the model's vocabulary smaller, more efficient, more adaptable.
So basic tokens are the raw bricks, but subword tokens are like more versatile Lego pieces.
That's a great analogy, yeah. They're more flexible, more adaptable building blocks, crucial for modern AI.
Okay, so these tokens, these bricks or Lego pieces, how are they actually used back in the old days of search, before all this fancy AI? How did we go from just words to finding documents?
Right, that takes us back. In traditional search, what we often call keyword-based search, or really token-based search, systems would break the text into these tokens, just like we discussed, but then they use them mainly to create a numerical representation called a sparse embedding.
Sparse embedding. Okay.
This was the standard way before we got into meaning, and its limitations really paved the way for what came next.
So what does sparse mean here?
Think of it like a massive checklist. A really, really long list, maybe tens of thousands of items long. Each spot on the list corresponds to one unique word or subword in a huge dictionary.
Okay, like every possible word.
Pretty much. And for any given document, most of the entries on that list are zero, because most words aren't in that specific document.
Ah, sparse meaning mostly empty. Mostly zeros.
Exactly. When a word is in the document, its spot on the list gets a number, usually just how many times it appeared.
So if my document uses the word cat 3 times, the cat spot on the list gets a 3.
Precisely. So a document becomes this huge vector, mostly zeros, with counts for the words it contains.
But what's the key thing here? The limitation.
The absolute crucial point, the thing that drove all the later research, is that these sparse embeddings don't understand meaning. They only care about frequency. How often does a word appear?
So car and automobile.
To the system, totally unrelated, unless you explicitly told it they were synonyms somehow. They're just different entries on that long list.
And bank. Like a river bank or a money bank.
It would treat them identically. Same token, same count, zero context. Huge ambiguity, often leading to irrelevant search results. It was stuck in a bag of words world.
Okay, that makes sense. So how did they generate these sparse embeddings? You mentioned algorithms.
Right. Classical algorithms were used, and some are still relevant. TF-IDF is a big one. Term frequency inverse document frequency.
TF-IDF.
Sounds complex.
The idea is pretty neat, actually. It gives more weight to words that are frequent in one specific document, but rare across all documents.
Fine.
Because if a word is common in just one document, it's likely a good clue about what that document is about. It boosts the importance score for those specific descriptive terms.
So not just frequency, but frequency relative to the whole collection.
Exactly.
Yeah.
Then there's BM25, which is like an improved version of TF-IDF, handles things like document length better. And newer ones like SPEDE, which uses neural networks but still creates sparse vectors, kind of bridging the old and new.
But fundamentally.
Fundamentally, they all boil down to word statistics. Frequency, distribution, not deep meaning. Historically, search was very deterministic. Index content as it comes in, count the words, decompose it lexically. Fast, efficient for the time, but brittle. Very different from today's semantic search.
Night and day. And to get to that semantic understanding, beyond just counting, we needed something completely different. We needed dense embeddings. That was the real paradigm shift.
Right, so tokens helped us count words, check frequency. Necessary first step. But counting isn't understanding. This is where embeddings, specifically dense embeddings, come in. They let systems grasp meaning, context, things sparse embeddings couldn't touch. So what exactly are these dense embeddings? How do they capture meaning?
Precisely. An embedding, a dense one, is also a numerical representation, a vector. But it's fundamentally different. Think of it as a unique fingerprint for a word, or even a whole text made of numbers. But these numbers describe semantic qualities.
Semantic qualities.
Yeah, the magic of dense embeddings is they capture semantic relationships and context. Imagine that multidimensional map again. Each word, each text is a point on this map.
Okay.
The closer 2 points are on this map, the more similar their meaning. Car and automobile would be plotted very close together. Car and tree would be far apart.
So the geometry, the distance and direction between points, actually means something about the relationship between words.
Exactly. The distance encodes semantic similarity. It's a geometric representation of meaning itself.
That's pretty cool. But why? Why do we need numbers? Why can't machines just read text like we do?
That's a fundamental point for machine learning.
Yep.
Most algorithms, deep down, they operate on numbers, not raw text. Human language is messy, ambiguous, full of nuance. Machines need structure. They need quantitative input.
So embeddings are the translators, language into numbers the algorithms can crunch.
Precisely. They're the crucial bridge. Translating qualitative language into quantitative data that models can learn from.
And how are these amazing meaning maps, these embeddings, created?
They're created by embedding models. These are often part of what we now call large language models, LLMs. The key is training them on absolutely massive amounts of text. Think Wikipedia, billions of web pages, books, conversations, just colossal data sets.
So they learn from seeing how words are actually used in context billions of times.
Exactly. That huge volume of data lets them learn the incredibly complex relationships between words. Synonyms, related concepts, how meaning changes with context, even subtle implications.
What's the process like? How does the training work?
It's quite involved. First, there's pre-processing. That includes tokenization, actually.
Ah, so tokens are still involved.
Yes, as a first step to break text down. Then things like lowercasing, removing common stop words like the way, is words that don't carry much unique meaning, sometimes stemming or lemmatization too, reducing words to their root form, so running, ran, runs all map back to run.
Cleaning up the text, basically.
Yeah. Then comes the sliding context window. It's like the model looks at a target word and the words immediately around it, its context.
Like putting it under a microscope with its neighbors?
Kind of, yeah, to learn how that word behaves in that specific neighborhood. Then, during training, the model gets tasks, like predicting a word based on its context. A common one is masked language modeling. Yeah, you give it a sentence with a word blanked out. The cat sat on the mask, and it has to predict the missing word.
Oh, right.
By doing this millions, billions of times, the model adjusts its internal numbers, its parameters. It learns to position words with similar meanings or uses close together in that high-dimensional map. It constantly refines the map to minimize its prediction errors. So doctor and hospital end up near each other. Doctor and tree end up far apart.
And you called them dense embeddings. Why dense compared to the sparse ones?
Because the resulting vectors, the numerical fingerprints, are mostly filled with non-zero numbers, unlike sparse vectors, which are mostly zeros.
So every number in the vector contributes something to the meaning.
Pretty much. It's a compact, information-rich representation. Subtle changes in the numbers reflect subtle changes in meaning. It's much more efficient for models to work with than those huge sparse lists.
Okay, so boiling it down for the listener, what's the big practical impact?
The big impact is that these models really understand meaning and context. So if you search for film, a system using dense embeddings can also return results for cinema or feature film because it knows they're semantically related.
Even if those exact words aren't in your query.
Exactly. Or searching for fast car could match quick automobile. It goes way beyond just matching keywords.
It's about understanding the intent behind the words.
Precisely, which leads to much better, more relevant, more intuitive search results. Much more human-like.
Here's where it gets really interesting then. Because that difference is huge. It's not just, is this word here? It's, what does this word mean here next to these other words? That's a massive leap in capability, from counting to comprehension. Okay, so you mentioned earlier, this isn't actually brand new for search, even though it feels like it with the AI boom. Google's obviously been a leader here. How did they integrate this stuff over the years? How did they get from basic keyword search to this?
Yeah, it's crucial to see this as an evolution, not a sudden flip. Google's been layering this tech into its search for, well, almost a decade now. It wasn't just a reaction to things like GPT, it was a long, strategic build. Maybe they seemed slow to some, but they were likely focused on making it work reliably at global scale.
So where did it start? What was the first big step?
The first really noticeable deep learning system was RankBrain back in 2015.
RankBrain, I remember that buzz.
Right. Even then, it was helping Google understand how words relate to concepts, moving beyond just keywords, especially for queries Google hadn't seen before, those weird, long conversational ones. RankBrain could sort of guess the underlying idea.
Like understanding the DeLorean time travel movie meant Back to the Future.
Exactly that kind of thing.
Yeah.
Using implicitly learned embeddings to connect the query concept to document concepts. A huge first step into semantics.
Okay, what came after RankBrain?
Next major step was neural matching in 2018.
Neuromatching.
This let Google understand how entire queries relate to entire pages, not just word-to-word matching. So, understanding that the query "best film for family movie night" conceptually matches a page titled "Top Family-Friendly Movies," even if the exact phrases differ.
Matching the overall intent to the overall topic.
Precisely, recognizing the semantic similarity between the whole query and the whole page content.
Then came BERT. Right.
Yeah.
That felt like a really big deal.
Oh, BERT in 2019 was massive. Bidirectional encoder representations from transformers.
Catchy name.
Yeah. But it was built on the transformer architecture, which was revolutionary. BERT helped Google grasp how combinations of words change meaning, especially word order and prepositions.
Like the difference between pharmacy to home and home to pharmacy.
Exactly, a crucial difference that older systems would miss. BERT could understand the context bidirectionally, looking at words both before and after a target word, understanding the whole sentence's nuance. Huge leap in natural language understanding.
And the MUM.
MUM, the Multitask Unified Model, arrived in 2021. Google said it was 1,000 times more powerful than BERT.
1,000 times.
Yeah.
Wow.
Yeah. MUM was a huge step because it wasn't just understanding language, it could generate it too, and crucially, it was multimodal,
Yeah.
meaning it could process text, images, audio, video, different types of information together.
So my search could understand pictures on a page, too.
Yes.
Yeah.
It could factor in information from images, maybe even video clips alongside the text. Plus, it was trained across 75 languages, transferring knowledge between them. That really kicked off the era of multimodal search. Everything, text, images, etc., potentially transformed into embeddings in one unified meaning space.
And this isn't just for my query, right?
Yeah.
The web pages themselves are embedded, too.
Absolutely. For fast retrieval, Google and others decompose documents into vector embeddings as well. It's how they index the web semantically. So your query gets turned into an embedding, and the system looks for document embeddings that are close to it in that semantic space. It's matching meaning to meaning.
That's an incredible evolution. Okay, so we've got tokens for counting, embeddings for meaning. Google's journey shows the power of embeddings. Let's really crystallize those core differences. Side by side, what separates tokens from dense embeddings?
Yeah, let's nail that down. A clear comparison really helps, especially before we talk about why you might need both. Thinking of it like that table from the source material helps. Okay, first, representation. A token is, raw text, a word, part of a word, punctuation, you can see it.
Tangible.
Right. An embedding, dense, is a numerical vector, abstract numbers in a high-dimensional space.
Right.
Quantitative, not symbolic.
Okay. Difference one. Text versus numbers.
Next, focus. Tokens are about frequency. How often does this word appear? Basic syntax. Dense embeddings are about semantic meaning and context. What does this word mean here? How does it relate to other ideas?
Meaning.
Got it.
Then similarity. Big difference here. With tokens, similarity means shared keywords. Same words, similar counts, similar documents.
Exact matches. With dense embeddings, similarity is about closeness in that meaning map, that vector space. Car and automobile are close because they mean similar things.
Conceptual closeness allows for synonyms, related ideas.
Exactly. Which leads to their main use. Tokens are for traditional keyword search, lexical search. Still useful for very specific, literal queries.
Find me exactly X17A gamma.
Right. Dense embeddings power semantic search. AI applications needing real understanding. NLP, Q&A, recommendations, generative AI. Understanding intent.
Understanding versus matching.
Then there's dimensionality. Token-based sparse vectors can be huge, tens, hundreds of thousands of dimensions, mostly zeros.
Sparse and wide.
Dense embeddings are smaller, hundreds or thousands of dimensions, but packed with non-zero values.
Dense and information-rich. More manageable for models.
Right. And finally, examples. Token-based, TF-IDF, BM25, SPLAID, statistical or neurally enhanced stats.
The classics.
Dense embeddings, early ones like Word2Vec, Glove, and the modern powerhouses, BERT, MUM, Gemini, context-aware AI model.
Okay, that comparison makes the shift crystal clear. From surface analysis to deep understanding. Which brings me back to that nagging question. If dense embeddings are so good, so powerful at understanding meaning, why on earth would we ever need to mix them with token-based search? Why not just go all in on embeddings?
That's the million-dollar question right now, isn't it? And it leads directly to why hybrid search is so critical, especially for robust AI, because even though semantic search with embeddings is amazing, it's not perfect. It has blind spots.
Blind spots, even with all that training data.
Yes. Specifically, it struggles to find similarities or retrieve information outside the domain it was trained on, or understand terms it's never encountered before.
Things it doesn't know.
Exactly. Hybrid search combines semantic search's understanding with token-based search's precision for those specific unknowns. It's about coverage and accuracy.
So who needs this? When is hybrid search essential?
You, the listener, definitely need it if you're building systems that interact with the real world, especially customers. Imagine an AI chatbot for your company. Customers might use weird internal codes, specific product numbers like SKU 9021EURB, or brand names that launched yesterday.
Stuff the main model couldn't possibly have seen during its general training.
Precisely. Or company jargon, niche technical terms. If your AI only uses semantic search, it might just fail. Say, I don't understand, or give a totally wrong answer.
Because it can't find a match in its learned meaning space.
Right. It struggles with this out-of-domain information. We even see hints of this sometimes when prompts for big models like Claude or ChatGPT seem to leak. They might be falling back on some form of keyword search to fetch specific facts they weren't explicitly trained on.
So things like product codes, error numbers, new brand names.
Those are perfect examples. A purely semantic search might just draw a blank. It needs that fallback.
The token-based search fallback.
Exactly. It uses token search to find those exact literal matches when the semantic search can't find a conceptual link.
So hybrid gives you the best of both.
That's the goal. Semantic search gives you broad understanding, high recall for related concepts. Keyword search gives you precision for specifics, high precision for exact matches, especially for those out-of-domain terms. You get comprehensive results. This became even more critical for Google, for instance, after they started rolling out things like the AI overview, blending generative AI with core search. They need both deep understanding and factual accuracy.
Which brings us back to that interesting question from the source material.
Right. Was this need for robust hybrid capabilities, ensuring reliability alongside semantic power, maybe part of why Google seemed to take its time fully integrating the latest AI wave into its main search?
It makes sense. They couldn't afford to break search at their scale. They needed the fallback.
It's a compelling thought. Balancing cutting-edge AI with bulletproof reliability for billions of users is, well, it's a massive engineering challenge.
That is a fantastic point.
Yeah.
The idea that even the most advanced AI needs that safety net, that fallback for the unknown or the brand new, it's a real eye-opener. It highlights the sheer complexity of building systems that can handle real-world language, which is always changing, always surprising. It's not just about being smart. It's about being resilient. Okay, so we've journeyed from tokens, the basic blocks, through embeddings and semantic understanding to the necessity of hybrid search for robustness. Now, looking ahead, AI agents are coming. What does all this mean for the future? For search, for content, for us? Let's try and summarize this deep dive.
Okay, let's tie it all together. Summarizing. Tokens are the fundamental lexical base. The individual units, the structure. Dense embeddings are the numerical representation of meaning and context, the rich map that captures semantic relationships.
Blocks versus meaning map.
Right. Modern search, modern AI, uses both. Hybrid search shows that. It needs the precision and the understanding. But the trend is undeniable. The focus is shifting heavily towards embeddings for advanced applications.
What way? What makes embeddings the clear winner for the future?
Because they allow models to grasp nuance, context, intent. They dramatically boost the reasoning ability of language models. They unlock that deeper comprehension. Moving from just seeing keywords to understanding concepts, relationships, even across languages and modalities like images, that's essential for conversational AI, generative models, complex decision-making.
So what does this mean for people working in this space? Search specialists, content creators.
It means our job is changing. A big part of our work now is structuring content and data so these systems can easily understand it, reason over it, synthesize it, and present it effectively, often in super personalized ways.
We need to think about how our content gets tokenized, yes, but more importantly, how it gets embedded, how it fits into that meaning space.
Exactly. We are right at the start of the AI agent era. These agents will do complex tasks for users' research, booking, analysis, and it's a vital thought. Our next client, the consumer of our content, might very well be one of these AI agents.
Wow. So we need to create content that's clear, context-rich, semantically unambiguous for machines to process and act on.
Precisely. Clarity, context, semantic richness are becoming paramount.
That's a really powerful thought to end on. From basic word counts to complex semantic maps, now hybrid systems powering intelligent agents. It's clear that understanding tokens and embeddings isn't just for engineers anymore. It's for anyone creating or consuming information in this digital world. The landscape is changing fast. So, wrapping up for you, our listener, we've unpacked tokens as the basic building blocks, explored how dense embeddings capture deep meaning, and understood why hybrid search combines both for real-world AI. It's a huge shift from just matching keywords to truly understanding intent and context. And as AI keeps evolving, becomes part of everything we do. Here's a final thought to mull over. What really stands out to you about how AI is changing the way we find information, and what could that mean for how we create it? How do we as humans adapt our own communication to be best understood by these incredibly smart but different systems where maybe our next reader is an AI agent and semantic clarity is everything? Thank you for joining us on this deep dive. Until next time, keep exploring, keep questioning, keep learning.